All right, everyone. So we are going to be working on a problem right now called the Soarin' Sky Coaster. So what we have here is, in the Sky Coaster amusement park ride, riders are suspended from a tower by two long cables. The lifting cable is then released, and the riders swing down in a circular arc. If the four riders have a total mass of 270 kilograms, what are the tensions in the two cables just before release? All right. So we have here our picture. I just already transferred that over to my sheet, which is the first step of making our free body diagrams, which we'll need to solve any force problem. So what I'm going to do next is circle the object of interest. So the object of interest for me right now is the riders, and I care about the tensions on the rider. So let's draw our free body diagram. I've got my particle right here. I've got some force of gravity acting downward. I've got a tension to the left. I'm going to call that T1. And a tension to the right. I'm going to call that T2. All right. We also know what angles these are at. The angle for T1 we know is 15 degrees. The angle for T2 is going to be 26 degrees. Now we have two different angles. So we need a way to distinguish one from another. So what I'm going to do is I'm going to call my 15-degree measurement the Greek letter phi. And then I'm going to call my 26-degree measurement the Greek letter theta. You can do phi and theta. You can do theta 1 and theta 2. Any way of distinguishing which angles are which is all we need to do here. All right, so my free body diagram is all set. From this, we can see that we're going to have x and y components. So if I wanted to, I could draw a second free body diagram with our weight down. We're going to have some y component of each of the tensions and some x component of each tension. All right. So next question is, where do we want to work? Do we want to work in the x or y planes first? Well, what do we have? We have the only variables we have are our angles and our gravitational force. Not our variables, but our knowns. So if I know this gravitational force, I'm going to want to work in the y direction first. So what I'm going to do is start by writing my relation here for forces. So I know my forces in the y need to cancel to 0 newtons. I know this because the ride is in rest. This is just before the riders are dropped. So my sum of the forces in the y is equal to T1 in the y plus T2 in the y plus our gravitational force, and that is still equal to 0 newtons. I don't like having T1 and T2 in the y here. I don't like that. That's kind of confusing. That's not what I'm solving for anyway. I'm solving for T1 and T2, not the y components of each. So I want to get these in terms of T1 and T2. The way I'll do that is with trigonometry here. If I want the y component, the vertical component of T1, I'm going to use sine of 15, my phi value. So I'll write T1y is equal to T1 times the sine of phi. Likewise, T2y will be T2 times the sine of theta. Fg is entirely in the y, so we can leave that as is. All right, I know I want to solve for my t's. I have that given, so I'm going to rearrange this a little bit so that we have T1 sine phi plus T2 sine theta is equal to negative FG. All right. I have an issue here, though. I have two unknowns in that equation. I can't go forward and just solve for those values. So what I have to do then is I'm going to have to solve for two different variables at the same time. The way I'll do that is I'm going to get one of the variables in terms of the other. I'm either going to get T1 to be in terms of T2 or get T2 to be in terms of T1. And the way I do that is I start solving for my forces in the X. So we'll start that right over here. Same thing. We are at rest. We know that. My net forces are T2x minus T1x is going to be equal to 0 newtons. I'm going to rearrange that so that we have T2 in the x is equal to T1 in the x. Same deal as over here with the y's. I want these in terms of T1 and T2, not T1 and T2 in the x. So I'm going to use trigonometry. T2 in the x is equal to T2 times cosine of theta. And T1x is equal to T1 cosine phi. Now I'm going to get one of these in terms of the other. So what I'm going to do is I'm going to get T2 to be in terms of T1. And the way I'm going to do that is I'm going to divide both sides by cosine theta. These will cancel here, so we'll have T2 is equal to T1 cosine phi divided by cosine theta. And that's true at any point in this problem. Well, at this exact moment we're looking at, really. That T2 is equal to our tension T1 times cosine of phi divided by cosine of theta. So with that, I can plug my T2 value here into T2 here. So we'll have T1 sine phi plus T1 cosine phi divided by cosine theta times sine theta. And that is equal to negative FG. I only have one variable here now, T1. I know my phis, I know my thetas, and I know FG. Or at least I know how to calculate FG, but we'll get to that in a second. So what I'm going to do here is I'm going to get T1 to be by itself on one side of the equation so I can solve for it. First thing I'm going to do is I'm going to pull T1 out using the distributive property. That'll give us T1 times sine phi plus cosine phi times sine theta divided by cosine theta equals negative FG. That then we're going to divide both sides by this whole mess of trigonometry here. So we'll have T1 is equal to negative FG divided by sine phi plus cosine phi times sine theta divided by cosine theta. What about FG? Remember, we weren't given weight. We were given mass. So our relationship that we use to calculate our force of gravity is shown here in the reference table as G equals Fg divided by m. Or if we want to rearrange it, like we did with our regular net force, we could say that Fg is equal to m times g. Which will get us our T1 as equal to negative mg over sine of phi plus cosine of phi times sine of theta divided by cosine of theta. All right. So now we finally have things we can plug and play for and figure out what our T1 actually is. So T1 is going to equal negative 270 kilograms. Notice how I'm still writing all my units, times negative 9.81 meters per second squared. That number wasn't given to us. We just know that because it's a constant we use. Times sine of 15 degrees plus cosine of 15 degrees times sine of 26 degrees divided by cosine of 26 degrees, which will get us a value for T1 of 3.6 times 10 to the 3 newtons. Or we can write that out as 3,600 newtons. Now that we have our T1 value, we can finally go back and solve for T2. And the way we're going to do this is we're going to take our T1 value we just solved for and plug it back into this equation here, our equation for T2 in terms of T1. Because now we know T1, we know our phi, and we know our theta. So I'll write this as T2 equals 3.6 times 10 to the 3 newtons times cosine of 15 degrees divided by cosine of 26 degrees. And this will get us a value for T2 of 3.9 times 10 to the 3 newtons, or 3,900 newtons. And that's our answer. So in this example, we saw that we had two different unknowns that we needed to solve for at the same time. So the way we do this anytime going forward generally is to get one of the variables in terms of the other, plug this into one of your equations, either the x or the y usually, solve out that one variable, and then plug that back into the equation you had set up for the one variable in terms of the other.